Welcome, folks. Today we're going to talk about periodicity. So we're going to be discussing a lot of the trends and habits that occur on the periodic table. Make sure you have yours with you today, and maybe a couple colors. We're actually going to get to make some good notes on our periodic table today. And if you don't want to draw on this periodic table, you can, of course, maybe take some notes or color in some things on a separate sheet. Or if you ever want like a blank periodic table, just let me know. I can get you one. First things first, though, the first part of Chapter 6, these first few pages are actually a review, and I'd like you to try and run through these on your own. So I'd like you to go through these. They're pretty straightforward. Run through each blank here and see if you can fill it in. Mine are all very poorly covered. And then when we get down here to ionization equations, I'd like you to do a little practice on your own. For cations, I'd like you to write the ionization equation for magnesium and aluminum. And for the anions, I'd like you to write one for oxygen and for bromine. And we'll go over these together in class just to make sure we're all in the right place. For our electron structure review, which is everything that we've been talking about this week, I'd like you to take chlorine and then do each level of structure for chlorine. Electron configuration, condensed, valence, orbital, and Lewis structure for chlorine. And just in case you don't remember, this one's a little trickier. Elements in the same vertical column, which is a group, in the periodic table have the same valence electron structure. So in other words, if we're looking at chlorine, the chlorine has 7 valence electrons. If we're looking at bromine, it also has 7 because it's right below it. Or something a little simpler, say for example like sodium. Sodium has 1 valence electron. It's, 3s1. Potassium below it is 4s1, 1 valence electron, so on and so forth. Okay? So, let's talk about periodic law. So the idea of periodic law is that the periodic table is set up in a very specific way, and that elements near each other on the periodic table actually have things in common. So many properties of the elements vary in a periodic way in their atomic number. So the way that the examples occur is usually up and down a group. So again, we call the group is the long one. It's like a column. Think of it like a column that holds up a building. That's a group. And some examples that we have here are things like in group 1, which is that first group of metals. We're going to talk about each group in detail. And the other example is things like noble gases. And there's a lot of different examples. So the different groups all have similarities in how they react, how they seek out electrons, things like that. It's arranged in a way that atomic number is what we count by. So when they first developed the periodic table, they actually organized it by atomic mass. But then later, another scientist came along and said, well, how about we organize it by atomic number? Because then if we do so, then we keep everything together that's similar in those groups. That's how we help form those groups. So if you actually look to kind of prove my point, because you might have thought that this was organized by mass. If you look on the table and say, for example, you find argon, number 39. And if you look at argon and look at argon's next element, which is potassium, you'll notice that argon has a higher mass than potassium does. This is only to prove that the table is actually organized by atomic number and it's not organized by atomic mass, okay? Because argon is at 39.95 and potassium is 39.1. So, let's talk about the regions of the periodic table. Before we start talking about the regions, we got to get a little vocab down. This is the way that we're going to refer to things on the table. First things first, periods are the horizontal rows going across. Think of it like rows in a movie theater, periodic periods, right? The groups or the families are the vertical columns, okay, the ones that go up and down, and they're numbered. So if we look on our periodic table that we have, you can see that the families or groups are already labeled with these different labels up here. 1, 2, 13, 14. Sometimes we just refer to the groups by using those A letters. So for example, group 17. Sometimes we don't call it group 17. Oftentimes we just refer to it as group 7. Sometimes we use the A, sometimes we don't. Just understand that they can be kind of both. We don't usually refer to the transition metals in groups because we often refer to them as just transition metals. But we also have the periods along the other side here, 1, 2, 3, 4, 5. It's kind kind of like coordinates, right? So if I told you that something was in group 2, period 5, you would know that I was talking about strontium. And that was kind of the point of organizing that in such a way. But each one of these groups has different characteristics. So our first group that we want to talk about is the transition metals. And the transition metals are any element that has a D block element, or that's the last electron that they fill. They fill in that D block element. And if we're looking at our periodic table, let me go ahead and clean this up a little bit. Let's see here. Our transition metals are these ones here in the middle. I got to get a big thing for this. I'm going to just color just like that. The most common valence for the transition metal block is +2, although there are more charges in the D block. The block that, or the charge that we see the most often is +2. They're less reactive than other metals, and they often form really highly colored compounds. So if you think about different metals, most metals are kind of like silver, but some metals can form really bright colors. So for example, copper, when it oxidizes and it goes through processes, it can form like a really bright blue color. And gold, of course, is like this lustrous gold, yellow, really, right? So they can form really bright colors. Next, we have what are called the inner transition metals. These ones have their electrons, their last electrons are placed in the F sublevel. And they are located in the periodic table, kind of jutting out of the transition metals. You see this section here that kind of juts out. Those are the inner transition metals. I'm going to move my noodle because it's in the way. And we can color those, let's see. We'll do one of them orange. These ones are the lanthanides. And in red here, I'm going to do the actinides. Now, they again are the inner transition metals. Let's go up and look. They are the lanthanides. And if you notice on your periodic table, the element that starts that column, number 57, before we go to 58, is lanthanum. So that's why it's called the lanthanides. And these are considered rare earth metals. And then there is actinium, which starts the actinides. And those are mostly man-made down at the bottom. The most abundant rare earth metal that we have, the non-man-made rare earth metal, is uranium. That's the one that is kind of, we found it in most abundance, like in our own earth, right? So let's see. We also have what's called the main group representative elements. So I'm not going to color these ones because they have their own different subgroups, but the main group representative elements are the ones that are on the sides. So again, anything that's in the P block or anything that's in the D or the S block, which is probably why this is probably not the right thing. Anything that's in the P block or in the S block are considered main group representative elements. Those are the main groups, okay? So, let's see. The last electron in these, as you can probably predict, are in the S or the P sublevel. And these themselves have their own special groups. And we'll kind of flip back and forth to make sure that we get those special groups. First things first, we have the alkali metals, which are in group 1. I would advise you to also take down the group just in case you don't color in your periodic table or anything like that. But let us list the alkali metals. They are in group 1, and I will do my alkali metals in blue. Why not? So these are my alkali metals. They're these ones here in group 1. Now they all are highly reactive. They are highly reactive because they only have one electron to lose, and they're going to really work to lose that electron because they really want to get rid of it. Just one? How easy is that? They're going to work hard to make sure that they can get rid of it. They have the alkaline earth metals, which are group 2. They are the neighboring ones. So group 2 is right here. Let's color those green. Why not? I'm just kind of picking colors. You can pick whatever colors you want. Those are the alkaline earth metals. They're group 2. They also all have similar properties. They are not as reactive. as the alkali metals, but they are still pretty reactive because they just want to get rid of those 2 electrons. Okay, we have the halogens, which are in group 7. Like I said before, sometimes we refer to it as group 17, sometimes we refer to it as group 7. So the halogens are right next to the noble gases, and very similarly to the alkali metals, the reasons why they're so reactive is because they really want to make sure that they can get just 1 more electron. That's all they need, and they're going to work really hard to get it. So here are the halogens. This one here in group 7. Things like fluorine and chlorine and bromine. Okay. And then finally, we have the noble gases, which I think I spelled noble like the man, Nobel, but it should be it should be noble gases, noble like royalty. And that is group 8. And we've talked a little bit about the noble gases already. The reasons why they're called the noble gases is because they are inert and they do not react with others, although the lower noble gases, the ones that are kind of lower on the table, are large enough that they can sometimes react with certain things, but otherwise they're inert. They don't need to react. They have as many electrons as they need. So let's keep going. Let's talk about properties a little bit. So let's get some concepts down. It's going to be a lot of conceptual stuff here. Please make sure that not only do you jot down whatever's in the blanks, but also kind of you can help yourself by jotting down the stuff that I'm talking about, because both are important. I'll try and make sure to write down as much as I can, but all things are important, not just the blanks, okay? So the metals themselves, let's talk about metals. Now, when I talk about metals, I don't mean if I were to ask you, like, give me a couple metals, I wouldn't want you to say, like, oh, like solid, liquid, or gas. Those are states of matter. When we're talking about different types of metals, we're talking about metals, non-metals, and metalloids. Those are the different things that are on the periodic table. So metals are good conductors of heat and electricity. We use them. They're often things that are on, the transition metal section or the alkali earth metal section. So the D block and the S block are usually the ones that are considered like capital M metals. They are shiny. Oh, well, they're lustrous, which is another word for shiny. They're both kind of the same thing. It's a metal's ability to reflect light, so most of the time they can be pretty lustrous. They are ductile, and they are also malleable. Now, to give you a definition of what these words mean, malleable means that it can be bent into a shape or flattened, and ductile means it can be pulled into wire. So let me write that. So again, these are properties of metals, that they can be bent or flattened or pulled into wire, which is great because we can then use metals for all sorts of things. They form cations pretty much exclusively. Not super exclusively, because the only always in chemistry is that there's always exceptions. But most of the time, they form cations. Just a few other things to add on to this. The colors that metals usually have, they're usually like gray or silver. There's a couple exceptions. Copper is that brassy color, and gold is that yellow color, but most of the time other metals are just usually kind of gray or silver. And then what else? Let's see. So if we talk about the state of matter of our solids, or excuse me, of our metals, they're primarily solid, except, can you think of one that is not a solid? It is mercury. If mercury is at room temperature, it is a liquid, which that's why we use mercury for things like thermometers and stuff. All right, let's talk about nonmetals. So nonmetals are kind of the opposite completely. They're poor heat and electrical conductors, which means that they serve as insulators. An insulator is just something that does not conduct heat or electricity. They typically form anions. They are trying to gain electrons. They're not trying to give them away. And if we talk a little bit about their states of matter, which is also important, they're mostly gases. And the reason why is because now we're including like the halogens and the noble gases, and a lot of those are gases, except bromine. Bromine is a liquid, which is pretty wild. So please keep that in mind. This is something to remember, that bromine is in liquid state. And metalloids are kind of in between, so you know which one the metalloids are. The metalloids are the ones that are on the zigzaggy line. So if we were to label them, these ones are the metalloids. So these ones that are resting on the zigzaggy line, those are the metalloids, okay? And astatine has like kind of metalloid properties as well, but the ones that are on the zigzaggy lines, those are the metalloids. And the metalloids are kind of in between. So they are semiconductors, meaning that they're not so great, but they're not so bad at making or conducting heat or electricity. And an example for this would be something like silicon. We use silicon for computer parts. Silicon is resistant enough, but can also heat up enough that we can use it for computers, which is why they call, like Silicon Valley, that's why they call it that. They're also kind of shiny, but they're not as shiny as metals. So, like I said, kind of in between. All right. So, let's talk for a second about periodic trends, and then we're going to be done. All right. So, the periodic table is set up in a really fantastic way. It's organized really excellently, and it also is organized in such a way that it illustrates trends. And at the bottom of this page, I encourage you to draw yourself your own little periodic table. I did it right here underneath metallic character. I encourage you to draw just a little one. It doesn't have to be filled in, but just kind of draw the shape because we're going to add content to it, and maybe that'll help you. Mine might be a little big, so maybe don't make yours as big as mine. I'm going to shrink mine a little bit. Oh no, I lost some lines. I'm going to fix it. I fixed it. All right, so let's talk about properties and their trends in the periodic table. First things first, let's talk about atomic size. All of the elements aren't the same size. They change size depending on their mass and depending on their radius. So remember, we're talking about those orbitals, right? We've been talking about that, how these orbitals take up a space. The orbitals also contribute to the atomic size. So the atomic size increases as you go down and to the left on the periodic table. So looking at your own, down and to the left, which means that the largest, biggest boy on the periodic table is francium. So I'd like you to add that to your little table. It might help you. Take an arrow or something and draw it down and to the left. And I'm going to label that arrow size. Right? So atomic size goes down and to the left. You get larger. Okay, let's keep going. Atomic size is also something that is affected by ionization. So whether or not something becomes positively charged or negatively charged. A positive ion are smaller than the neutral atom they form from, and a negative ion are larger than the neutral atom they form from. This kind of lines up with what we would probably consider. If I were to have an orbital or some sort of ion, or some sort of neutral something, and I were to pluck an electron off of it, making it positive, then it's less electrons, right? Which means it's smaller. And the same thing, if I were to add electrons on top of it, then it would be more electrons than you used to have, which means it would become larger. So I think that kind of lines up with what we think. So just keep that in mind. If it becomes positive, it's smaller than what it used to. And if it becomes negative, it becomes larger than what it used to be, which again is kind of backwards. But the reason why is because we're adding electrons, okay? So let's talk about our next form, which is called ionization energy. Ionization energy has a really important definition. It's an incredibly important value for us to measure. Specifically, it is the energy required in removing an electron from an atom. So it's not just free to pull electrons off atoms. Sometimes they are okay with it, and other times they don't want to lose electrons at all. So ionization energy is something that each successive ionization energy increases as we pluck electrons off. So for example, if I were to label my ionization energy as IE, and my ionization energy 1, meaning the ionization energy required for me to pluck off a single electron, ionization energy 1 is much smaller than ionization energy 2, meaning the energy required for me to pluck off 2 electrons. And therefore, just kind of keeping going, ionization energy 3 is also much higher than ionization energy 2. So I always kind of think of this like plucking, like plucking the electrons off of the atom. So if you pluck once, the atom's like, stop. But if you pluck another time, it's even that much harder. And the third one is even that much harder to pluck off, because every time an electron is plucked off, all of the other electrons get closer and closer to the nucleus because they become more and more condensed. So it's that much harder to pull them off. Some elements don't allow for the first one to get plucked off. Some have a hard time plucking off more than one. So if it's a neutral atom, the trend here is that we increase as we go up and to the right on the periodic table. So this is opposite of size, which is down and to the left, up and to the right of the periodic table. Let's go ahead and go down to our little that little periodic table we made, and let's add in this arrow. So again, it's up and to the right, which means the element that has the highest ionization energy on the table are the noble gases, helium, right? It's up and to the right. That's the direction in which we increase in ionization energy. Similarly, we also have this idea of electronegativity. Electronegativity is defined as the tendency of an element to gain electrons. But I'd like to also add an additional definition to this to kind of help us understand what electronegativity means. It's also what I would call the ability of an atom to attract electrons. So the ability of an atom to attract electrons. I think both are great definitions of what we're talking about here with electronegativity. So the tendency of an element to gain electrons and the ability of an atom to attract electrons. So it's an atom's ability to bring electrons towards it. It's kind of like how hungry an atom is for electrons. Like, man, I just really got to get those electrons. I'm going crazy for them. I'm going to take them. That's what electronegativity is. So electronegativity increases also as you go up and to the right. But in this case, we exclude the noble gases. We do not acknowledge the noble gases. So let's put one more arrow here. And I'm just going to put this arrow a little bit off this time. And let us label this arrow as electronegativity. I don't think I spelled it right. Tivity. There we go. I stopped short. There it is. Electronegativity. So now we have all three trends, up and to the right. And then we have another one, metallic character. Metallic character, an element becomes more metallic as you go down and to the left. This one isn't as important, but we can add it to our table. It pretty just much means that as we get lower on the table, the more metallic our elements become. So they have more of a metallic characteristic. For example, if you look at row 4, we start at the top with carbon, we go down to silicon, which is a metalloid, we go down to germanium, which is a metalloid, then tin, which is just a metal, and then lead, which is also a metal. So as we have continued downwards, we become more metal-like. We have more of those metallic characteristics. Now, one last little thing that we want to talk about. Let's talk about how we can identify some physical properties of different elements based on the information of elements around them. So let me show you what this looks like. So say, for example, I want to determine the melting point of an unknown something. And this unknown something is palladium, which is what PD is. I do not know what the melting point is of palladium, but I do know that the melting point of nickel is 1,453. And I know that the melting point of platinum is 1,172. Now here comes the numbers. Let's find nickel, platinum, and palladium on our periodic table. If you look on your periodic table, they're all in the same row, right? Nickel and platinum are above and below palladium. So we could probably take the average of those two numbers and then try and use that average as kind of like an estimated or predicted value. I want you to give it a shot. Take the average of those two and see what you get. Okay, so if you took the average of 1772 and you add those two numbers together and divide by 2, the average you should get is about 1613, which means that that is our predicted melting point. Well, the actual melting point of palladium is 1552, which is pretty close. I'd say it's not so bad, considering that it's just a guess. It does kind of help us get kind of in the ballpark. And let's look at this other one here. Let's talk about density. So we have hafnium, we have tactinium, and we have tungsten, right? So we're going to look at the density of those three. What if we said that hafnium had a density of 13.1, tactinium had a density of 16.6, and we do not know what the density of tungsten is, right? So we want to try and figure out, if we can figure out, what tungsten's density is. Hafnium, tactinium, and tungsten are all next to each other on the periodic table, one after the other. So we can kind of use this as a way to maybe guess if the difference between the two is the rate in which they're increasing, well then maybe that rate is the same. So if we were to take the difference between the two, we would find that the difference is about 3.5, okay? So if we add that 3.5 to that 16.6, we would get 20.1 as our predicted value. So again, that 3.5 is the difference. It's 16.6 minus 3.1. That's our predicted value. Our actual density for tungsten is 19.3, which is pretty close. It's actually a lot closer than the other one. So it goes to show that there actually is value in this. We can use these as a way to assume the physical properties of neighboring elements. That's it, folks. That's chapter 6. Did it all in one go. We'll see you in the next chapter.